Okay, so here we're trying to find the maximum area where we have a rectangle and it's gonna basically be inscribed or basically like trapped within an ellipse, like an oval. So it's basically gonna have its corners on the ellipse. So let's just draw what we got going on here in case you need a little refresher, because maybe you didn't spend too much time dealing with ellipses, it's actually really not that heavily covered in Algebra 2 anymore. It's at least where I teach. But it's not too hard to understand it if you know what a circle is. So this is basically a circle stretched out in the x direction because you have a bigger number under x. That's usually how I tell my students to remember. So I'm trying to draw this without screwing up. So it's going to be something like this. Something like this, and it'll have intersects at 12, 0, 0, 0, not 0, 0, 4. Negative 4. Negative 12, 0. And so your rectangle is going to be trapped within it, and this ellipse is centered at the origin, so it's going to be symmetric in all 4 quadrants. So we can just let's look at this one coordinate, or this one upper right hand corner with its coordinates be x, y. So we want to find the values of x, y. Where would you have to put that corner of a rectangle so that you get the biggest area in that total rectangle? Now, to make this just easier to work with, let's just focus on one of the rectangles, or 1/4 of the entire rectangle, because this is going to be symmetric in all 4 quadrants because it's centered at the origin. So if you just find the area of the one of the rectangles, then you could basically know the area of the entire rectangle because you just multiply by 4. So let's basically look at what would x and y have to be so we get this top right rectangle to have the biggest area. Now, since we have a rectangle here, we know that the area of a rectangle should be no surprise, is just the base times height, length times width, or we can just say x times y, x, y. But we are going to need to have an equation for area in terms of one variable, because the idea is to differentiate area so that we can find the optimum values of area with respect to one of the variables, and then we can study that value and see if it is going to be a max or min or what's going on there. But first we need to write area in terms of just one variable, so let's write it in terms of just x. And so for that, we're just going to basically rewrite this equation in terms of y, and then substitute it into here. So basically, doing our algebra, solving this for y, subtracting, we'll get y squared over 16 equals 1 minus x squared, 144. Multiplying each of these by 16 and then square rooting, we'll get y is equal to the square root of 16 minus, so you have 16x squared over 144, and that'll just reduce to x squared over 9, because 144, or 16 goes into 144 nicely, perfectly 9 times. So I should write that over 9. So now I have an equation for y. Then I plug this equation for y into here. And I get my equation for area to just be equal to x times the square root of 16 minus x squared over 9. Now I have my primary equation that I can work with. Right up here, little star. So I'm going to differentiate this equation with respect to x find the critical values, and make sure that that critical value is going to help us figure out if it's a maximum. Hopefully it's a maximum, so our lives will be easy. If not, we can see where the maximum or minimums or what's going on with the function. But let's first find the derivative of this function with respect to x. We're finding dA dx. And that'll be pencil. We're going to use the product rule because we have one function here times the square root function, the derivative of x, which is just 1. Leave the square root function as is, so it's times the square root of 16 minus x squared over 9. Plus, and then we have this x function stays constant times the derivative of the square root function, which is the same as raising something to the 1/2. So it'll be 1/2 times 16 minus x squared over 9, so negative 1/2. And we're going to multiply this by the derivative of the inside, which would be negative 2x over 9. So let's rewrite this a little easier, cleaner to work, so that's easier to work with. Well, dA dx will be square root of 16 minus x squared over 9. So we're going to have a plus. These 2's will cancel. Plus, plus, minus. We're going to have a minus. This will be the square root function in the denominator. We're going to have this in the bottom. So we'll have on top x squared over the square root of 16 minus x squared over 9. I'm going to put these both in parentheses so they're easier to read. Now, what I need to do to make this easier to figure out the critical values of, is I'm going to combine these terms. So I'm going to make this have the same denominator as this one. So I'm going to multiply this by this over this. So I'm going to go through it step by step because I want to make sure that you can see it clearly, because sometimes this algebra part will be the part that'll screw up. Like calc students, it won't be like, oh, it won't actually be the calculus part. But so this first part we're going to have 16 minus x squared over 9. Remember, that's just a fraction. It could be all over 1. Now multiply that by the square root of 16 minus x squared over 9 over the square root of 16 over the 16 minus x squared over 9. 9 times that whole thing minus this again. So working it out, keeping it going, dA dx will be equal to, on top here, since I multiplied the same thing by the same thing, I'm going to have, oh, and actually I missed something. That was close. I missed this 9 in the denominator here. Oh, not a problem, not a problem. I'm going to throw that 9 here, 9 times that. Times 9 there. So what I'm actually doing is multiplying this. So here we have a 9 times that. Multiply that by 9 times that over 9 times that. So it just means adding that 9. That. So they're all going to have a denominator of the 9 times this thing. So let me just put it all over that. Denominator of 9 times the square root 16 minus x squared over 9, like that. Now on top, I'm going to have 9. You have the same square root being multiplied by itself here. So the square roots cancel, so all you have is 16 minus x squared over 9 in parentheses. You multiply by 9, and then you're subtracting that x squared up here. All that is on top. This becomes equivalent to, we distribute that 9 to the 16 and the x squared. You know, we're going to get 144 minus a 9x squared over a 9, or minus x squared, essentially. Minus x squared minus x squared. Let me distribute that. That becomes minus x squared, and then minus, so we have minus x squared minus x squared, so we just have on top minus 2x squared. There. All over the 9 times the square root of 16 minus x squared over 9. So now we have an equation for the derivative that, that we can work with. Because the goal, remember, is to find critical values here. So we want to find where the derivative could be equal to 0. So we basically just got to set the top equal to 0. So we set 0 equal to 144 minus 2x squared. Solving this, we'll get minus 2x squared, 72x squared. The square root of 72 will be 72, and then x will be the square root of 72, or you can reduce it as, 6 root 2. Their critical value. So we'll start by, it's important, critical value. Now, now it's like, well, how do we let's look at other possible values. This is like going to be like, where should I use first derivative test, second derivative test? Like, what should I do here? Well, let's think about this. So remember, we also want to find where this would be undefined. This will be undefined when 16 minus x squared over 9 is equal to 0, because then you would be divided by 0. But if you think about it and look, well, just actually do the math, this is going to occur when x squared, when this is 144, because 144 over 16 is going to be 16. There we go, it's proven it. So this is going to occur when x is 12, or when x is negative 12. Now, but let's look at what is going on with our rectangle here. Remember, the ellipse only goes out to 12, 0. So if the x value was 0, or if the x value was 12, the ellipse, let me see if I can use a different color here. Well, the rectangle would just be this flat line. It wouldn't be anything. It would have no area. So that's, this is not going to really work. This is not going to be in our domain. And what's the other? What if x is, what's the other possible endpoint? If x is 0 up here, right? It would then, be nothing. It would be up here, it'd be this vertical line, right? And we're talking just this top rectangle. So then, if this is a critical value, then we know, because going from 0 to 12, the area has to get bigger, because when you just intuitively, as you're going along this, edge, you're going to be making a rectangle. Let's just look at hypothetically, you're going to be making a rectangle bigger and bigger until you get beyond a certain point where you start decreasing. Once you get beyond this point, this optimum point 6 root 2, your area gets smaller and smaller until it gets that flat line. So the optimum here, the biggest value, or the biggest area that you'll get, will be when x equals 6 root 2. So be when x equals 6 root 2, that'll be the biggest or optimum or maximum area you'll have. So x will be 6 root 2. Then that means for this to be technically correct, remember we're only talking about this half. The total, the total base of this rectangle from here to here will just be, let's just say width will be 2 times this. So 2 times 6 root 2 or 12 root 2. And then the height or the y value, the phone's going off. So, my bad. The height, the y value, you can just figure out what it'll be by plugging the x value into here. And then that'll be basically 2 root 2. This will be 2 root 2 when you evaluate it here. But then when you find the total height, it'll be twice that value, and you'll get 4 root 2 for the total height. But again, just in this small rectangle, we're only talking about the 6 root 2 part, and the height will be 2 root 2, but if we want to actually be technically correct, the whole rectangle, just double the height and double the width, and you get that. And so there you go.